I can hear you great. Yeah.
Awesome. Perfect. So
Thanks, Steve.
yeah. Okay. Yeah, maybe yeah, we can just start from here.
So should we put it like full screen or something?
Yeah, this is the full screen now, and I think this will be good. Yeah, maybe we can test. Yeah.
I can move it down using this. No, this is not.
I think it will be good for now. Yeah, will be good. Yeah. Yeah, good. Awesome. Awesome. Yeah, yeah. So we just maybe with one more minutes we can get started. Maybe I can see here. People will see also here. So you
I
may
don't
have.
need to speak much. Let's see. Today's the title and this don't be printed by. Let's see.
Yeah, yeah.
My Vijay Gupta. Let's get started.
Okay, cool.
Really good.
Yeah. Hi, let's get started. It's 2 o'clock, and thank you very much for coming here in person and also join us online. So today we have two events, and first is our regular weekly ICON seminar, and we have a second event, and I will leave my colleague to introduce the second event later. So let's get started for the first one. So today it's our pleasure to have Professor Vijay Gupta to give us a seminar about distributed synthesis for local controller in networked systems. And Professor Vijay Gupta, he's a professor in School of Electrical Computer Engineering, and he received a bachelor's degree at the Institute of India of Technology, and a master and PhD degree from California Institute of Technology, all in electrical engineering. And he received 2018 Antonio Ruberti Award from Actuary Control System Society and a couple of other awards. So without further ado, let's welcome our speaker, Professor Vijay Gupta. Yeah. Oh, the other one didn't show up. Let's see. Oh, laptop. Oh, maybe this one as well. Yeah. Yes, it works. Awesome. So just do we need to record somewhere? So we will record the seminar. So just, can we record seminar? Okay, let's do that. Sorry about that. Where is the option recording?
Looks like it's already recording you.
Oh, yeah. Yeah, shares will be helpful. It will be awesome if you can help me record. Oh, it's already recording.
Sorry.
Okay. Awesome. Let's get started. Yeah.
All right. Thank you very much. Thank you very much. Thank you very much for the kind introduction, and thank you to ICON for giving me the opportunity to talk about some of my work. So this talk really has two aims. I want to introduce some of the work that I do, but also, since there are a lot of students here, I wanted to say a little bit about my perspective on some interesting open questions in the field, and why one may make an impact working on those kinds of systems. So this is joint work with a lot of former students and colleagues, former students and present colleagues, and I would like to acknowledge them. So for a long time, distributed or network dynamical systems have been considered in our community, right? So papers and transactions and automatic control go back on distributed systems, go back at least to the 1960s. I did not search in 1950s, but I'm pretty sure that there would be some systems there. The applications that are of interest keep changing. In the 80s, there was a lot of work on platooning, distributed computing. When I was a student, sensor networks were very hot. Then, vehicle formations and going up to swarms, very large swarms. Even systems that we think of as single systems, like a car, really has a lot of decision loops, control and decision loops that have to coordinate with each other. The lane changing controller and the cruise controller and the cannot fight amongst each other to take over the operation of the car. And if you project tomorrow, we can think about even systems of systems, where power grid will interact with transportation network and so on. In any distributed system, the challenge is always we want guarantees on global behavior, the behavior of the entire system, but we want to make decisions locally, where we want to have local communication or information processing and information exchange. Okay. So as I said, people have looked at it for at least 40, 50 years in our community, and a very rich theory of distributed control is available, right? So people know how to characterize stability of linear distributed systems, goes back to 70s and 80s, decentralized fixed modes and all that. Classification of cases where efficient design, control design is possible, notions like quadratic invariance, partially nested, again, a long history and ongoing work. Numerical algorithms for controller design when efficient optimal design is not possible. And recently, people have also realized that if models are not known and so on, multi-agent reinforcement learning provides a very rich set of tools, very powerful set of tools to solve this problem. So one question may be, well, is there anything new in this field, right? And since I'm going to talk for at least an hour about this, there should be something new and exciting. So here's a motivating example that might sort of set the stage for the kind of issues that I'm going to talk about. So people have talked about how to make power grid resilient. And one of the central things that comes about is that we may think of power grid as a network of smaller microgrids, right? So Purdue University can have its local generation and local load and local controller. And so can the next sort of community and so on. And if, for example, a storm comes and some line goes down, we just think of this as separate islanded microgrids, and we serve the local loads the best we can. And so, right? So the problem is that the topology of the entire system at any time is unknown, right? If there is a storm or something, Purdue does not know whether Lebanon is connected to Indianapolis or not, right? Certainly, we do not know detailed models of what is connected, what loads are being served, what is the local renewable generation that is happening at that moment, and so on. Yet, stability of the entire system depends on us knowing those quantities, right? If power in equals power out has to hold for the entire network, not just locally from a microgrid. Okay, so this is a distributed control problem, right? I have to control how much power I'm putting in and how much loads I have, how much power I'm consuming. But the guarantee that I want is for the entire system when I do not even know what the system looks like or what the other controllers are doing, what the other parts of the system are doing. Right? So if we appeal to distributed and decentralized control theory that I talked about, it kind of falls short here, right? So for one, that theory talks a lot about distributed implementation of controllers that when I'm calculating the control input, needs information only from my local neighbors, but does not talk about distributed design of controllers. The design of controller is still done by a centralized agent who has accurate knowledge of all the dynamics and interconnection topology, and who can rest assured that all the subsystems are cooperative, are not trying to be strategic and optimize some local cost function. They will follow whatever I tell them to follow. So in this case, that is not true, right? Purdue might only be interested in serving the loads at Purdue for the most part, right? The accurate knowledge of subsystem dynamics or interconnection topology may not be available, and what we certainly want is a local design. Okay? So perhaps a question of interest then is not only obtaining guarantees on global behavior through local control, but local design and updates of controls when the subsystems may possibly be self-interested and possibly unknown. Okay, and if you think about going towards these larger scale systems like infrastructure systems or swarms, which are which have hundreds or thousands of vehicles, then these kinds of questions become more and more interesting, just for scalability purposes, or even just because of the terrain in which we are operating or the particular application that we are concerned about. So I'm going to talk about essentially this question and our work in dealing with this, and again, I'll come back to a couple of questions that, that within this field we're still not sure how to do. Okay, so this is the outline. I'll talk essentially about two sets of results. In the first set of result is more towards my roots as a classical control person. So I'll talk, essentially, I'll show that system theoretic notions that are classic in some sense, in this case, dissipativity and passivity, that shape energy profile of a system, can be used for this compositional design that is local, that does not require knowledge of the entire system. Even with, even with these constraints that we want the design to be local, these can be used. So I'll talk about that in two parts. One is I'll talk about how do I design passivity indices or dissipativity notions for subsystems in a compositional manner when my object is system stability. Then I'll talk about what about performance, and performance is a difficult subject in distributed control, so I will not be able to give a full answer, but what I will come back to is perhaps we can, how can we interface these more classical notions with recent learning-based controllers to try to get some notion of performance. And a question that always comes up is, why don't we just give up on classical control and just do, for example, multi-agent reinforcement learning? That is entirely local, and maybe that can work. And there are, multi-agent reinforcement learning certainly is a very rich set of tools. And I think it has a very big place in future control. But there are some challenges there. Some challenges were addressed by Xiaoxuan in last week's beautiful presentation. I talk about a slightly different challenge, that of fragility to strategic agents. I do not know if I will reach there in how much detail I will be able to do this because of time constraints, but let's see. Let's get started.
So just 1 second. I forgot to open the video so that the online people can see you. Sorry about that. Here, yeah. So then online people will see you talk. Sorry about that. Yeah, I think that is good. Thank you.
All right, so let's get started with the first talk. And here, I'll be talking about sort of using dissipativity notions for compositional design. I'll be talking about passivity indices. So just a brief refresher of what passivity is. So dissipativity, or its special case passivity, formalizes the notion that a system dissipates energy. So if we have an electrical circuit and there's a resistance in it, or a mechanical system, it has friction in it, it dissipates energy. And while Lyapunov theory formalizes that notion for autonomous systems that do not have external inputs, dissipativity essentially does it for systems that have inputs. Right? So if we talk about energy being stored through a storage function Vx, being supplied from an input W and an output Y, so think about this as voltage times current, for instance, so it's power. External supplies, and then dissipated energy essentially should be greater than 0, and we formalize that through an integral of this. Right? So the energy being stored should be less than the energy being supplied. So some energy is being lost to them back. Right? You can also do it in discrete time. And in particular, passivity means that your supply rate is of the form U transpose Y. Again, think about voltage times current. Right? And passivity is nice because if you can show that a system is passive, it is stable under mild conditions. And also passivity is compositional. So if I take two stable systems and put them in feedback, they need not be stable, but passive systems in feedback. And so it's a limitation on stability. It's a smaller set, but it's a nice. And then you can take this notion about passivity indices to quantify how passive a system is. So if you think about this equation, this is essentially an equation U transpose Y. So in single input, single output case, it's somehow saying something about the system remaining in the first and the third quadrants. And if a system is very passive, then you kind of take lines and say this system is very passive. This system lacks passivity, but sort of. And then you can use passivity indices to compensate for lack of passivity of plant like very passive. Right? So it may not be passive. I design a very passive controller, and in feedback, I will be passive and hence stable. You can reason about these things using passivity indices. So the first part of the talk, I will forget about this notion of self-interested and unknown. So I'll still assume that my controllers are completely cooperative. They are all interested in maintaining the system stability. And I'll be talking about how can I design passivity indices for subsystems through this local a process in a compositional manner for system stability. Okay, so I'll be talking about sort of linear models. Nothing that I have, I will say cannot be done for nonlinear. It's just easier to talk in terms of linear because we get nicer conditions, more crisp conditions. Okay? So think about subsystems. Each subsystem has state X that evolves as such. Vi here is the coupling from the other subsystems. So think about all the subsystems in a set according to this graph. And so they are all feeding in its states through some coupling terms. Wi is the external disturbance input, and Ui is the control input that I get to design, and Yi is my output. Okay. So I can stack everything up and talk about this network state system. The only thing that's interesting here is capital N, which is an index of how many systems there are. So this is according to a certain graph. Okay. So what are the existing approaches for stability without centralized design? As I said, the core of distributed control has been centralized design. So if I take this linear system, for instance, and I ask, can I design a U that satisfies the constraints on whose state I have access to, only my neighbors according to that graph? Can I stabilize the system or not? Question that was addressed in the 70s by, for example, by Anderson and Moore and also other researchers. But what was I saying? But if I don't allow that, if I want every subsystem to design its controller without knowing what faraway agents are doing, then the system is not. Then this answer is not. Okay. I can also have systems joining in and coming out. And again, if you look at the core of the centralized theory, if a new system comes in, the sigma n+1 comes in, even the controllers at faraway nodes, they're not talking to sigma n+1, have to be updated. The entire system has to be, you have to restart the design process. Okay. So can you be more efficient? So there are some works that have tackled this problem. One can assume that the solutions, the system has weak coupling. Right? So intuitively, the coupling is weak. You kind of don't really care about systems far away. Right? But that kind of defeats the purpose, right? If in a microgrid example, if I'm not really transferring a lot of energy from one microgrid to another, why do I have the network at all? It defeats the purpose. You can have decomposition-based solutions, you can have hierarchical approaches, and so on, but sort of most of them, again, either lead to weak coupling or assume a central guy who is coordinating the solutions and so on. So this question of how to design subsystem controllers using only local information. So sigma 23 should only know about 21, 13, and 24, should not know about sigma 1. How do we do that? It remains still open. Okay. So there'll be going to be a bunch of slides which are perhaps a little bit dry. So let me just give the observation of how the control will work. So if I think about the original notion of passivity or dissipativity, the point was that the system is going to be passive and hence stable if the energy being supplied from the external and energy being stored satisfy a certain relation. The system should not sort of generate energy in a state. It should be dissipating energy like a resistor or a friction. Here, I can kind of argue the same thing. The system will be stable if every subsystem is dissipating energy, except that the energy that is being stored need not be stored only in the system itself, but can also be stored in the interconnections. When two systems are dynamically coupled, right? Think about masses and springs, the spring can also store energy. So as long as I can keep track of that, I will be able to use local conditions on how much energy is being dissipated by this subsystem. Just kind of keep track of all the subsystems locally, okay? only in my own dynamics and my own couplings, and I'll still be safe. Right? So the next few slides are essentially saying that if I take energy dissipated by standalone, not connected, energy stored in the connections. So the easiest thing to think about are springs, for instance. Then as long as I can do bookkeeping of energy that is supplied from external and energy that is stored locally and in interconnections, I'm safe. The rest of the thing is just bookkeeping at this point. That's the basic idea. Yeah. So essentially, you start from a centralized relation, and this is where the linearity is helpful. If the system is nonlinear, you'll not get these LMIs, but you'll have to check for dissipativity. So if I take the entire system, I'll get a LMI of this form, which will be enough for passivity. But this is the entire system approach. This is somebody, a controller, knowing the entire system, right? This A system encodes the entire system. I don't want that, right? In a swarm, I only want local decisions being made with local information. So I can show that a condition for that is that every subsystem I satisfies the condition of this. So let's parse this a little bit. So what, instead of this giant matrix being positive definite, I want this system to be, this matrix Mi to be definite, which Mi is defined as such. So for the first system, the system that I start with at the beginning, the first subsystem does not need to worry about any of the systems. So μIS is something very similar to that equation. Okay, so this μIS is just that. And then the other systems need to worry about μIC, which is out here. And the only thing I will point out is that this encodes the coupling. This is where the bookkeeping of the energy in the interconnections is. Okay. Precisely how do you obtain this? You can read the paper and so on. But it's the same intuition that I just said, that you have to keep track of the local energy and energy that is being stored in the interconnections, which we do through this medium. Okay. So the algorithm kind of becomes like this, right? So the first system, it does not matter how you number the systems, by the way. I'll just use for any numbering. Any numbering would work for feasibility. So you start from any subsystem. This system does not know anything about the other subsystems. All it needs to do is make sure that it is dissipated, that it is giving out energy. It's dissipating energy, right? So we check the local condition. If that is not dissipative, we can design a local controller to make it dissipative. That's still local linear matrix inequality. Then what we need to do is compute this matrix μIC, which says for the next system that is coming, this is the amount of energy that I'll be storing in the coupling. Okay, it stores that. Then the second guy comes in, the second subsystem. All it needs from its local neighbors is how much energy it is storing in the local coupling. Once it does that, it can check its own dissipative condition that based on its dynamics and the energy that system one is giving it through the interconnection, it is dissipative. If not, design a controller. And then it figures out for the next system, whether it's sigma 4 or sigma 3, how much energy is going to give out. Okay. So you can keep doing that. 3 does that. And sequentially, by using only the information from the subsystems that I'm dynamically coupled to, I can figure out how much energy do I need to. So I am changing the profile, energy profile of the entire system based only on talking to systems that I'm already dynamically connected. Any system that comes in later, 3 comes in later, 2 does not need to change anything based on that. Okay. If 4 comes in, now it needs to talk to 1, 2, and 3, and so on, right? So nth comes in, n does not need to talk to 1, right? 3 does not need to talk to 1, for instance. It's not dynamically coupled. If a new subsystem comes in, suppose all the n subsystems were living happily, system was stable, everything was done, n plus 1 comes in, it starts talking to n. All it needs to assume is this matrix Mn, which I call an essential matrix, and design locally, right? The other systems are not affected because they were already dissipating sufficient energy to make themselves stable. So if you go back to our motivating example, kind of this works. Plots are not particularly interesting, but if you think about 3 connecting to DG1 and 2, and then disconnecting, the controller for the second one does not change. Only the local redesign happens, and we still sort of go back to wherever the goal is quite nicely. So this works. Okay, so this was if the models of the systems are known, especially if you are linear systems, then you get nice linear matrix inequalities. If the model is known, then you can guarantee stability in this compositional model. Okay. Now, what if the model is unknown? Right. So also it might be that I have a controller that my subsystem already has based on some learning algorithm or something, some MPC or something. So how do I then impose this passivity constraint on the system? So I'll be talking about 2 things. One is more classical system identification based, I want to identify a system such that I can design this controller to have dissipativity constraint. And then later I'll talk about an optimization, possibly learning-based control. Okay. So our job is, I have this subsystem whose model I do not know. From the first part of the talk, I have been told that I need to design a controller such that the closed loop subsystem satisfies a certain passivity constraint. How do I do that? That's my job. Okay. So the first approach I said, you can identify the model. Right? So here's some possibly nonlinear system. You can identify the system from data. You can get an approximate linear system model and then use that for control. So problem there. And this is typically what is used in control, right? You get a subsystem system, you identify it. The problem is that there is no method in the literature that can guarantee from the passivity properties of the approximate from the identified system what the passivity properties of the original system is. There's absolutely no method. Okay. When we do identification, we make sure that our system is close, the learned system is close to the correct system in an input-output sense, but we lose every guarantee on any control relevant property, where it's passivity, positivity. Does my system? So suppose my nonlinear system is a chemical reaction. I take its properties, I take its input-output data, I learn a model. It may lead to densities becoming negative. I lose all such properties. Okay. We just hand wave, or we just pray, or we just hope that our system is close enough so our control techniques, any controller that we design using this applies. But in this case especially, since we want to have a closed loop passivity index, I want a guarantee on what is the passivity index of the original nonlinear system or the open loop system. Then I can design a controller for the closed system, right? So how do I obtain a linear model that is itself passive, but more interestingly, it guarantees a passivity index for the original system? I can just impose a passivity constraint on standard identification, like a subspace identification or something, but that will be a horribly nonlinear, non-efficient problem. And again, it will not yield any guarantee. But passivity of this system implies passivity of that system. So this is actually a gap, and again, kind of getting on my professorial thing about students and open directions. How do I combine system identification, which is a very, very rich theory and very nice set of tools, with control-oriented models, properties that I want that are useful for control design, passivity, positivity, monotonicity? How do I combine the two is a very open problem, and for students who are looking for problems might be something that that will trigger some thoughts. So our approach here is essentially that I will learn a system model, and then I'll perturb this matrix C. So C was the system matrix that I learned, and then I'll perturb it to the extent that I get a passive system. And this perturbation approach, if I do the perturbation carefully, passivity of this system will give some guarantee to the passivity of that system, position system. Okay, so this theory was actually in passive circuit modeling. It was in transactions on circuit design and so on that this theory had appeared, and we basically applied it to a more general system. Essentially, the result is kind of like this, right? So if I learn this system, if I keep perturbing it delta C till I get a passive system, let us say that, remember this cone system, right? The cone was related to how passive the system is. Right? So if this system is related to, is passive to this section, it's very passive, then the original system, the maximum nonlinearity, I can get a worst case bound, how much non-passive could it be? Once I get this bound, I have available classical techniques to design a controller so that the closed loop system becomes passive or satisfies a certain passivity index, which was used in the first part to guarantee that the system is stable. Okay, so by perturbing this, I can not only get a passive system model here, but I can get guarantees on the original nonlinear system as well, which I can then use for control design. So I will call this control relevant identification. So here is how I would use it, right? So I have, let's say, a simple circuit. I learn a baseline model. This is not passive. Original system is passive. I know that. There's resistance in there. So I learn a perturbed model. I keep perturbing the C, and at gamma equals 9.53, I get as a system. And the interesting thing is that I get guarantees on how non-passive the system is. So I can use this model to design a controller, and I can get passivity indices of this controller guarantee sort of the closed loop system remains passive, even though the system might change a little bit. So this is a model-based approach in some sense. I learned the model and I learn a control element model. And the bigger direction that I'm proposing here is how do I do it just for other control element properties? And I don't know that, but if some of you have any ideas or this sparks your interest, please come talk to me. I'll be very happy to exchange some. Yes, sir.
So how do you choose delta C in this example?
So we do it a dumb way. We just start doing gamma times this and start increasing gamma till it becomes passive.
So you're basically doing this.
Yeah.
So if you were to actually do a constraint optimization of the system identification and compare it to this solution,
This would be very conservative.
this would be much better.
Yeah, but the constraint one would learn a passive model, but it would not give any guarantee on how passive the original system is. This gives us a guarantee on how passive the original system is.
Is there a theorem that tells you?
Yes. It's this theorem,
No,
the theorem version of that.
saying that if you do a constraint optimization for the system identification, then you don't necessarily have a passive solution.
There are counterexamples actually. So you can do, instead of this dump search that I said, you can, do more interesting perturbations by this data bounded by IQCs and so on, right? And this just to show that not everything here is the first thing that came out to our mind kind of thing. You can do something more interesting. All right, so this is one approach. I learn the model, I learn a controlled element model and use that. The other might be that I use a controller that perhaps does not use the model, reinforcement learning, because an optimization-based model that already has a model. There's no point in me going and learning another model. So one way to think about the next part is if you are excited about reinforcement learning, I give you a system, you go and design your reinforcement learning based controller. Then I come back and say, well, this controller is very nice, but what I would like you to do is also ensure that the closed loop system is dissipated. Right? Perhaps you can replace dissipative by it's positive, it's monotonic, it is safe, it is this, that, but in this case, dissipative. So I want, how should I perturb an RL algorithm that is not under my control? The subsystem can choose whatever RL algorithm it has, but now I want to change it. I want to guide it so that the closed loop system satisfies a control element property, in this case, dissipative. Yeah. So process, controller, standard sort of RL framework, right? And the system can be nonlinear and so on. I have shifted my notation already, and so why not keep shifting and keep go down that path. So in this case, I'm saying we aim to choose a control policy, so A, such that the system is dissipated from the input input new to output y bar. Okay. And remember, the sort of the dissipative condition was given this. So you can do that. That's the main result is that you can do that, and you can do that through this tool of control barrier functions that have been recently proposed for system safety. Okay. So the first observation is that what I want to do is, if I look at the dissipativity notion, there is this energy that is being supplied that has to be greater than 0. So I convert that into forward invariance of this function. So this function is forward invariant. The set greater than equal to 0 is forward invariant. Then I can show that it is dissipated. This is the condition on input and output. And so I can use control barrier function based approach to say that if my control is chosen from the set such that this condition is satisfied at every time step, right? So I'm standing here and I say my next control input should be such that whatever energy has been sort of supplied so far minus the energy that is being supplied is greater than or equal to 0, I can show that my system is will be dissipated. I don't care how this is being generated. I just say if my control input satisfies this, I'm safe. Okay. So if I was designing the control policy from scratch, I can directly say this is the control policy I want. Right? If my RL is designing this, then I can have something like this. So forget about the previous CDF controller just for some details. Think about an RL controller. It gives me some control input. What I would do is I would generate this set and project my input to that set. Okay. I can project it, sort of generate this controller, dissipativity ensuring controller, by projecting it by the minimum amount, and the minimum amount turns out to be a quadratic program. And so at every time step, I don't care what the RL controller is, the inner workings of RL controller is. I don't even know the utility function of it, right? So they might be self-interested and whatever the utility function is. All I do is take that control input and keep projecting it onto the set. Notice that if I'm thinking in the context, original context, the distributed system, different subsystems might have different reinforcement learning controllers. So we don't make any assumption of either knowing the cost or dictating to them what reinforcement learning algorithm they should use. Everybody can do this. And once you do that, so your control input, the reinforcement learning is this, you project it, kind of go back and either explore from this side, or you can kind of keep exploring here. And ultimately, you sort of train your algorithms using this. So you can get a theorem which says that the closed loop system will be dissipative, and if you make certain assumptions about the reinforcement learning algorithms, then you can get some how much performance guarantee that how much performance are you giving up because of this. Okay, so again, the example is not. So the point here again is that we have combined sort of a learning-based controller or an optimization-based controller. This might be an MPC or something, without the need of learning the model ourselves, using a classical sort of control tool to get guarantees now on system performance. Okay. The control barrier function was a tool that was used for essentially state-based constraints, and here we have used it for input-output constraints. So there was some technical jugglery that had to be done, but that's not the main message. The main message is that perhaps looking at reinforcement learning not as a magical tool to just give us a controller no matter what is happening, but combining it with some of the tools that we have been using, we as control community have been using for many, many decades, and that have shown power in our problems. But combining the two can yield something that is even bigger. Right? Here it was dissipativity, but there might be other ways of ensuring these properties, and also other properties that we might be interested in that can give us. So, for example, monotonicity has been used to show safety in a variety of constraints. With reinforcement learning, as just done as a black box, we don't have any guarantee of monotonicity. Can we use that? Can we combine that? So control relevant learning, I guess, is what I would call it. And again, I think that this is a very interesting direction for students and so on. Okay, so in the remaining kind of 10-15 minutes, what I would go to is the second part, where essentially I say, well, so far we have been doing essentially what a control person would do, right? I mean, learn the system, design a controller, think of this as a distributed control. Why did just throw this away and just say, let's run reinforcement learning, multi-agent reinforcement learning. If everybody is cooperative, if people are not cooperative, let's do game-based learning. And learning algorithm will learn some controller for us. So what's the problem with that? Okay. And as I said, I'll point out one problem, which is that if our agents are, if our subsystems are self-interested, then there might be an issue with the standard algorithms. Okay. So I'll start with right? So learning algorithms are very powerful. I'm not bad-mouthing them. They are very attractive for designing optimal policies. In cooperative systems that share the same utility function, for instance, they can be used for distributed design. Yes, it is distributed design through multi-agent reinforcement learning. Even when people don't share the same utility functions, they can be used to learn strategies that the agents should play at some equilibrium, typically Nash, but also Markov effect and so on. And the message of the second part of this talk is that such learning algorithms may be fragile to strategic agents in the sense that I will describe, and hence an open direction, I think, for us as control people who understand notions of fragility and robustness and so on, is to design resilient learning algorithms. Okay, so I'll start with multi-agent reinforcement learning. So what is multi-agent reinforcement learning? So in a single agent reinforcement learning, environment is the plant, agent is the controller. I want to learn a policy pi of generating control action A given the state S, where the reward is R. So I want to maximize something infinite horizon reward. I want to calculate single agent reinforcement learning. Multi-agent reinforcement learning is that there are lots of agents. Think of this as subsystem controllers, right? Different controllers are there. And each of them has some action, and the state transitions based on all the actions. So their individual rewards might be R1 to Rn, and they might be the same or different or whatever. Since my reward depends on the state, which is a function of all your actions, I need to observe both the state and also what you guys are doing. Right? So typically we assume that the global state is observable, but the agents may not view each other's rewards or actions. That sets up the difficulty in the problem. In a cooperative setting, which is what I'll focus on, cooperative multi-agent reinforcement learning, agents want to maximize the sum of the rewards. So they share a reward, right? So they have a total team utility that reward. So they must communicate. So if I do, like, let's say, gradient-based method to optimize my policy, I want to move from policy pi to pi plus 1, pi of t plus 1, in the direction that it improves the performance, right? But remember that the performance is related to the sum of everybody's rewards, in the agent index, right? So I don't know what other rewards other people are getting, so I cannot directly calculate this. And so this was an open problem, and Kaishin Zhang in 2018 proposed that I can estimate this. Essentially, the intuition is that this is like an average, so I can do a consensus algorithm. Right? So what he proposed was that the agent I does a stochastic update and also consensus update. This consensus update really makes sure that the gradient that I'm calculating, I'm doing it in the correct direction by taking that direct team into account. So what he proposed that if it's a fully cooperative network, the sort of consensus update is being done, and if the network is undirected, let's say, then I converge to the global, to the optimal of the entire construction. Okay. Now, what if there is an adversary or a strategic agent? One of the agents does not care about the team. So the problem needs to be posed a little bit carefully, right? Because if all that the strategic agent wants to do is that nobody should converge, that's very easy. I can just transmit garbage at every time step, and consensus will not converge, and so algorithm will not converge. So instead, let's consider a more interesting strategic agent that is not interested in the team objective. All I want as a strategic agent is my reward function, right? All of you want the team. I want myself. Okay. So what happens? So I can communicate whatever I want arbitrarily. So what happens in this algorithm? Okay. So we can show that what happens is that all agents evaluate the value function as the strategic agent, or this adversary's value function, rather than the team value function. And then they seek to optimize the value function only of the agent. So I can derive a lot of rent, right? Not only am I taking the action myself to optimize my thing without caring about you, I can ask you now to take actions to optimize my thing. So that's fragile in the sense that no matter how many good agents there are, if there is a single strategic agent, the algorithm doesn't work. Everybody ends up optimizing the self-strategic agents. Okay. So think about this example, a grid world example. There are 5 agents. They want to go to the blue position, and without an adversary, while avoiding collisions, without the strategic agent, all of the agents go there. But if one is a strategic agent, only one reaches where it wants, right? And in fact, all the other agents move out of the way to avoid collisions. So they end up helping one. So, without the adversary, once reward kind of grew like this, it's in a really nice spot. It can convert very, very quickly. All the other agents are off, right? And it's fragile in the sense that it doesn't matter if I keep adding agents that I know are good. It doesn't matter. One bad agent spoils the entire system. So we have done some work for resilient MAL, and this is related to Dr. Sundaram's work on resilient consensus, right? At the core is the fragility of the consensus algorithm itself, right? And that's the proofs are a little bit more algebraic, some more algebraic jugglery is involved, but essentially the problem is the same. So, following up on Dr. Sundaram's work, what we do is we ask each agent, when it's doing this consensus update, to throw away the extreme values that its neighbors want to be sent, right? So if a neighbor is strategic and it wants everybody to go to an extreme agent, at some point, it will not be sending values that are close to what other agents are doing. And so we throw it away. So then the strategic agent cannot do arbitrarily bad things. It has to make sense, right? And we can show that the algorithm is resilient in the sense that the agents converge to a policy that is within the neighborhood of the correct policy, provided that the network is connected. So this is a resilient MAL in the sense that it solves the problem we had, but is this enough for control or not? Right. So if you're using this maximizing a convex combination of utility functions, is it still stabilizing or not? Does it give any guarantee on how bad we can be? It's an open question, and if you have any ideas on how to approach this, I would be very eager to hear that. Yeah. And the very final thing that I want to do is sort of go away from this. Everything so far was in a cooperative setting, to go a little bit into a game theoretic setting, right? So in a game, we have these subsystems that are coupled to each other, right? So my reward function depends on what you are doing, but I don't care at all about the team functions. Everything is out in the open. Right? So here, everybody was caring about the team except the strategy. Let's just get rid of that caring about the team. Everybody cares about their own, right? So one can pose games, and learning in games has been widely used to identify solution strategies, right? So you kind of say, when will I converge to an equilibrium, right? Whether it's Nash or Markov perfect, depending on the game that you have. So I can think of this as a plant, two controllers. These are the two players in the game. I have my strategy of how should I do. I play, I observe the payoff, I update my strategy, and do I converge or not? So it's very similar to learning. And in fact, if the game is complicated enough, you do end up at reinforcement learning in a slightly different context. It's not multi-agent reinforcement learning. We are not looking at team function. Everybody is interested in their own utility function, but we converge to an equilibrium, right? If the game is nice enough. So a popular learning algorithm here for simple games is fictitious play. So in fictitious play, what happens is that I keep a record of all the actions that were played by the opponent. Okay, so far we were playing rock, paper, scissors, and you played rock 30 times, paper 50 times, scissors 20 times. So I convert that to a histogram and assume you will follow in the next game, you will play according to that strategy. Okay, and I play my best response and keep doing that. And if the game is nice enough, for example, if it's a potential game or so on, then you can show that this very simple idea actually converges to the Nash. Okay, so I'm playing to a fictitious strategy, a strategy that I think you are doing. Well, you're not really doing that. And remember that you are also updating. So it's a very highly non-stationary thing. I'm updating my histogram and my strategy, and you're updating your histogram and your strategy. And there are guarantees on convergence for various kinds of games, and even 2005 and so on. This is an interesting. Okay. So the question that I want to pose is the same, right? So here agents are already strategic. There is not even a notion of team, right? We are all out in the open. I care about myself, you care about yours. But when we come to this learning algorithm, there is still cooperation. In what sense is the cooperation? in the sense that I am following fictitious play and you are playing fictitious play. We both agree that even though we are strategic, we care only about ourselves, it might be a zero-sum game, I win, you lose, but we'll still do fictitious play. That's a cooperation, right? So the question is, can a strategic agent do better than a Nash equilibrium by exploiting this fact that you are doing fictitious play? Let me confuse you by playing something else and then move the game to an equilibrium that I like. Right? And so, for example, in this game, the Nash equilibrium is 2-1. The row player has at least 2 other columns that it wants to be and get better payoff than 2. Can it do that? And well, it can. So that's the interesting thing. Well, that's perhaps not too difficult to see it can. The interesting thing is that it can do better than a leader-follower strategy also. It can do better than a statistical strategy also. And we can sort of identify a linear program to identify this mixed strategy. Payoff opponents may or may not be increased, and so on. So I'll kind of go back and sort of close the talk now. Distributed control is a very classical topic, right? But I think there is a lot of assumptions that are made in the literature that now time has come as we talk about larger and larger systems, swarms of huge number of vehicles and so on. We talk about scalability or not knowing individual subsystem dynamics, their utility function, not being wanting to do the design at a central place, but want sort of resilience or performance to be obtained by local design. And sort of we covered some of those things. So we covered compositional design for or local design for stability in these constraints. And essentially the message there was that the tools that have been used in classical control in sort of model-based settings can be extended to compositional control, but also for learning these settings. And I've identified the need for learning-based combining identification and learning and control together to be able to get guarantees in the system. We also considered in the second part learning algorithms that may be useful for control, and in fact probably are useful for control, but then we need to consider some of the consideration that we have as control engineers about robustness and resilience to these learning algorithms and solve these problems. So that's all I had. Thank you very much for your attention, and I'll be happy to take questions.
Any questions? So yeah.
I have a question. So about the last part of your talk, is it possible for one of the players to identify that the opponent is not going to play as they keep playing the game?
Very interesting question. So you can do some sort of meta learning is a word, but it's kind of like learning what learning algorithm the other person is doing. So if you identify, so what we have is a limited version, right? So what we have is if you define a class of learning algorithms in which you have an index essentially of how far in the history I'm going for this histogram, then we have some resumption. In general, because the learning algorithm can be arbitrary, to identify what learning algorithm the other person is using, I think is a difficult one. Whether I can detect if it is fictitious play or not, that's probably more to it. I don't have an answer, but I think it's very interesting.
There are more questions from audience here, or questions from online attendance. Is there any question from online attendant?
I had a quick question. Hey, Vijay, for the first part where you're designing the controllers in a distributed way to get passivity, is there a way to overlay other performance metrics on top of that? So if you want to say, get passivity as a baseline just to ensure stability, and then you want to optimize around it, is there a guidance on how to do that?
Yeah, so very, very good question. So
Can you restate the question?
Yeah, so the question is that in the very first part, I'm only interested in stability. What about performance? Is there some way to also get performance guarantees? So getting performance guarantees, even in the classical setting where I can do centralized design, is in general a very difficult problem in distributed control. right? So what is the optimal controller, or what is the performance that is achievable? Okay, so the closest we have come to this is in this thing where we're saying you might have an existing controller for reinforcement learning or model predictive controller based. So that is taking care of performance, and then you constrain it by the minimal amount to also guarantee stability, right? We still don't have a theorem which says by this approach, this is the performance you'll be able to obtain. I mean, I had that theorem for RL, but that is not very practical to apply because I don't know what the unconstrained algorithm is giving me. But if you have a handle on that, then you can get a handle on what the projection is limiting you. So it's not. So we do not have an answer to what is the optimal performance that you can achieve with this additional constraint in place, because the underlying problem, even without the constraint, is not solved yet. But you can have performance optimizing controllers, and then on top of that, you can just sort of limit this without sort of guarantees, for example. You still get guarantees on stability, but you lose guarantees on performance.
Great, thanks.
Hey, Vijay, this thing. Yeah, follow on these questions, because I'm also thinking that the passivity formulation is good. It just say if we're only, at the first step, right? If we're only considering about stability, but typically, if we want to have even not an optimal performance, let me just say, even our traditional, how fast I want certain things to converge, or these kind of things, this response speed type of things. It's going to be a little bit difficult to answer with this specific formulation, right? So one more, you just mentioned that, okay, you might combine this one as just use the passivity formulation as a constraint, and in combination with other model-based control design. I'm not sure how that will work out, because say, when we talk about nonlinear systems, right? And you have passivity formulation, and I also have the final ones to be able to show the converging rate or that kind of things. I'm going to have the detailed system oriented the other formulations. We do have connections there, but they pretty much, let me see, either I'm not sure. Just say they are two ways of approaching the control design. I'm not sure how you can combine these two and constrain. Just say you have a design with a model-based control design, and then later on you constrain with the persistent formulation. I'm not sure how we can accomplish that. And can you give me a hand on that?
Yeah, thank you for the question. So the question is there a clean way to combine model-based optimal control with kind of this passivity-based framework? And so in general, as you well know, that the answer is no. But that is because of a couple of things, right? So even with the model perfectly known and no constraints, optimal design of nonlinear systems or optimal design for distributed systems is an open problem, right? So if you are additionally putting constraints on top, then getting guarantees on performance is going to be difficult. Now, I did talk about a couple of ways in which you can, if you have a controller that optimizes performance. So for example, if you're identifying the model, you can use the identified model in an MPC framework. And then on top of that, you can just constrain the passivity using the method that I said by perturbation and then learning the passivity indices to guarantee stability. So you can put in optimization-based controllers there to get some notion of performance and still retain these guarantees on stability, but certainly identifying what, characterizing what the performance is difficult, because, for nonlinear controller and distributed systems, it's difficult anyway, even without constraints.
Hey, then I think due to time limit, maybe we can leave all the questions after this session, so we can discuss later. So I think this first session for seminar will be we will conclude the first session. Let's thank Professor Vijay Gupta. So next, maybe Shaoshai will introduce our next session.
Yeah, sure.
And thank you very much for VG for the seminar. And now is our seminar section is finished. So all students, you are feel free to leave. And we'll enter our next section, icon faculty and staff visitors. So I will ask our staff visitors, especially Dr. Patrick, come to the front and go. And also icon faculty. Should we close this one? Yeah. Hi, all online attendants. So our seminar will be ended now. So I'm going to close Zoom. So we are having the second session about some communication with please feel free to stop by in the conference room. So thank you for your attention. So I'm going to close here.